right, there. Hello, encoding overload. Consider turning. Okay. Streaming. Hey, we're streaming. Okay, hey everybody. Welcome to Phys111 Electronic Office Hours. The questions are listed below. We're doing a variety of questions for Chapter 2 because that's what this week's homework is on. And we'll also be applying lots of the things that we've been talking about in class. Let me bring the mic closer. Okay, can you hear me now? How's that? I checked that mic health. 1, 2, 3. Yeah, that's a little bit better. So we're going to be covering things that are a lot closer to the material that we've been doing in class. There's some more challenging stuff. If you have a question or you can't see something properly or you'd like me to go over something else, make a comment in the comment bar on the live chat, and then what's the bar called? Yeah, live chat. And yeah, so let's get going on this. One. Okay. Without further ado, turn to Chapter 2. This is in the black textbook, so fetch out your black textbooks. I'll read the question aloud, but I'm not going to write out everything in it just because, you know, copyright. Question 7. If you walk 3.2 kilometers to the supermarket, then back home, what's your distance traveled and what's your displacement? So this particular question is about the difference between displacement and distance traveled. I'll draw you a picture. So if this is your home and this is the supermarket, what is it? 3.2 kilometers. Oof. So first you walk there, and then you walk back. The total distance traveled is, of course, 3.2 plus 3.2, so that's 6.4 kilometers. But what's the displacement? How do we calculate the displacement? To calculate the displacement, we can do a couple things. But the overall displacement is going to be the vector from my initial position to my final position. Okay? Delta x. It's obviously 0. The displacement away from home is 0. That's not tricky. The way to see this, though, is to go, okay, so the first jaunt is plus 3.2, and the second jaunt is back home, it's minus 3.2. So the overall displacement is going to be the first one plus the second one, which is 3.2, no, it's plus 3.2 plus minus 3.2, which is 0. So there's a couple ways to calculate it. There's a couple different ways to explain it. Ooh, the stream health is yellow. That's not my favorite color. But I don't know. Can you hear me? Is everything good? I think things are okay. Okay. The stream's on a slight delay, so make sure everything's cool. All right, next question, I guess. Question 18. So if you have questions about what we do, just pop it into the live chat. 18 says the following. Buffering. Video output low. Okay, you know what? I'm going to pause right now. I'm going to check my streaming settings. I thought I had them set well, but the YouTube's complaining about it. So hold on, please. And stream pause. right, we're back, I think. We're supposed to be back. So, hopefully this is working. I believe it should be. Yeah. I don't know. Dropping frames. Who knows? Okay, well, I don't know. Or somebody here knew, but nobody knows. So we'll just keep on going. Keep on going. Okay, so I guess let's start the next question. Question 18. Buffering. Okay, figure P2.18 shows motion of an object as a function of time. How long did it take the object to get from the position x is equal to 2 meters to the position x equals 3 meters? Is there only one correct answer? So the graph looks like this. 20, 40, 60, 80, 100, and 1, 2, 3, 4. It's in your books. No, don't be straight. Give me a curvy line. All right. So there's a lazy ass drawing of what the line looks like. So the question goes, in this diagram, how long did it take to get from 2 meters to 3 meters? Let me draw it in red. So at these times, I'm at 2 meters. And at these times, I'm at 3 meters. So the question's asking, essentially this is an interpretation question. How are we going to interpret this bonkers diagram? And the idea here is that it's saying, hey, how much time does it take to go from here, when it's at 2 meters, to here, where it's at 3 meters? The issue here is that, I don't know, which time are we talking about? It's also at 3 meters there, that time. It's also 3 meters that time. It's also 3 meters at that time. Are we talking about this time interval, or are we talking about this time interval, or are we talking about this time interval, or are we talking about this time interval? So it's kind of ambiguous. And that, I think that's the answer to the question, that it's ambiguous. So that's fun. Next question, question 29. 29. These early physics book questions are always bonkers because they're like, I don't know. They can't assume you know enough physics. Okay, so question 29 says, figure 2.29 shows position as a function of time for two cars traveling along the same highway. At what instant are the two cars next to each other? At what instant are they traveling at the same speed? Here's what the graph looks like for the two of them. So one car looks like this, and another car's motion looks like this. Okay. So I'm going to draw on this to answer the question. At what time are they at the same position? Well, when are the cars next to each other? They're next to each other when they're in the same position. So they're in the same position at this time, and they're at the same position at this time. Okay. At what time are they going at the same speed? Well, the thing about speed is it's the slope on this diagram. Well, it's the absolute value of the slope, to be honest. So in this case, they're both positive all the time. So the speed is going to be the same as the velocity. But it's about slope, right? So this one has a constant velocity, constant speed. Oops, I don't like that. Delete. But the other one has a velocity that changes. So when is the instantaneous velocity of this dark blue line the same as the instantaneous velocity of the light blue line? And to see that, you just draw a bunch of tangent lines, and you're like, yeah, that's too shallow. What about over here? No, that's too steep. So there's a point somewhere in the middle here where they're parallel, where the tangent line and this line are parallel. And at that moment, they're traveling at the same speed. So whatever that time is, T4. Okay? Any questions? Nobody said anything on the chat, so I'm going to presume no questions. I'm also going to presume that you can hear me. I think you can hear me. Let me type in the chat, see if people can hear me. I moved the window around. Okay. Can you hear my voice? Question. One person on the chat, I don't know if they're going to reply. I guess we'll go to question 35 now. So question 35 looks like this. You're going to visit your grandparents who live 500 kilometers away. As you drive on the freeway, your speed is a constant 100 kilometers an hour. Half an hour after you leave home, your brother discovers that you forgot your wallet. He jumps into his car and speeds after you. The two of you arrive at your grandparents' house the same instant. What's your brother's average speed for the trip? This is a lovely question, in part because there's a bunch of different ways you can go about solving this question. So let's see. Let's start by drawing a motion diagram. So this is my home at x equals 0. And this is my grandparents' home. And they live at x is equal to, ooh, that was weird, 500 kilometers. Let me scroll up the screen here. Okay. So, the deal here is that I'm going to move along at a constant velocity like that. How much time is it going to take me to get there? I don't know. Let's see, 100 kilometers an hour, probably 5 hours. My brother, on the other hand, is going to leave the house at a slightly different time. Hold on. So this is t is equal to 0. T is equal to 1, 2, 3, 4. Oh, just whatever. Motion diagrams are... Nobody uses them. I just use them to teach. I'll draw a graph. Graphs are easy to talk about. So what I'm going to do, the way I'm going to crack this problem is I'm just going to draw graphs, and then I'm going to use the graph to derive some equations. And so we're going to crack it in two different ways. 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. So that's time. I'm going to start at t is equal to 0 hours. And then this is 1, 2, 3, 4, 5 kilometers. 500, 400, 300. Okay, so the stream is janky. Oh, it went offline again. Hold on, I'm gonna reboot the stream. One, two, three, four, five. All right, stream's back up and running. Okay, so all I'm doing right now is I'm drawing this graph. You know, I thought we could do this on graph paper. I don't know what the story is. I gotta figure that out. All right, so here's essentially my position versus time. It's a straight line from t is equal to 0, 500. So it's, let's see, you go x me is equal to the y-intercept here is 0. I start at 0. So it's going to be 0 plus 100 times t. And that's in kilometers per hour. And then time is in hours. Okay. Now my brother is also going to travel at a constant velocity. And he wants to arrive exactly when I do. So he wants to, in his position versus timeline, needs to intersect my position versus timeline at exactly that time. Oh God. YouTube, what's your problem? Last year we had no problems doing this. This year everything's a big baby town. Alright. So I need to intersect. So when the two lines intersect, it means that they're in the same place. Like in this diagram here, right? Same place, same place. My brother's going to travel at a constant velocity, so it's going to be a straight line. So I need to draw a straight line that intersects mine at that time. This isn't the only clue I have, though. I've also been told that, let's see, 35. That a half hour after I leave home, my brother discovers I forgot my wallet. So half an hour after I leave home, that's at 0.5 hours. My brother is here. X is equal to 0, that's my home. And at this point in time, he leaves. And so his trajectory is going to be a constant velocity line like that. So the question here is, what's his velocity going to be? And it's not that tricky, actually. I can find his velocity straight off this graph if I want to, right? Because I know that let's do it in red. I know what the rise is. I know that that's plus 500. And I also know what the run is. That's 4.5 hours. So the average velocity is going to be 500 over 4.5. Where's Calculon? Calculon. Oh, did I bring him to class today? Jeez, where's my calculator? Well, the feed's perfectly healthy when I lose my calculator. Did I lose my ding-dong calculator in class today? I think I brought it to the lecture. One of the lectures. Should be around here somewhere. Jeez, they cost a nickel. How can I lose it all the time? Oh, I don't want to use those. Oh, that's an okay one. Alright, found one. You might wonder where I get calculators from. Short answer is... lots of people lose theirs in final exams. That's 111 kilometers per hour. Ta-da! And that's the answer to the question, right? That's my brother's average speed. It's also my brother's average velocity. I guess they haven't specified which direction is which, but whatever, it's fine. Okay, so now it's question 55. How do we do question 55? Question 55 goes, a bug on a windowsill walks 10 millimeters per second from left to right, 120 millimeters, slows to millimeters per second, and continues to the right for another 3 seconds, stops for 4 seconds, then walks back to its starting position at 8 millimeters per second. So first we need to draw the x-coordinate of the bug's displacement, and then find its velocity. Oh, that's fun. Why is it offline? This thing says I'm streaming. Oh, there. Okay. We're good. We're good-ish. Hello. Welcome back. All right, let's go through this question. So, long story short, if you have any idea about how to fix all of my streaming problems, improving my stream health, or any valuable input, I will welcome it. Okay, so let's get on to the next question. The next question goes, where was it? Bug on a windowsill walks 10 millimeters from the left to the right. All right, let's just start by drawing it. Here's our bug. And then so, oh, son of a, 1, 2. All right. So I'm gonna sketch what the bug's doing in each step. First, they go like this to the right for a bunch, and then they slow down, and then they stop, and then they walk back home. So the question here is asking us to draw a graph based on the information it provided. So, hold on. Is it possible to do this with graph paper? No. Graph paper. Oh, that's a game changer. Okay. So, let me erase this poorly drawn axes. Whoa, you can erase the graph paper. Oh, no, you can't. Okay. All right. All right. So it's moving 12 seconds, and then 13, 14, 15, and then 19 seconds, and then so I guess I'll go to, I don't know, 30 seconds. Sure, why not? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Oh, good. 30. All right, so we can just do t in seconds in the natural unit. All right, what about this vertical thing? They move to 120, 10 millimeters per second for 120 millimeters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Huh. So I'll call this 10 millimeters, 20, 30, 40, 50, 60, 70, 80, 90, 100, 101, 102, 34. Oh, someone's at the door. Probably to yell at me about my poor streaming. Yes, hello.
Hi, just came to pick up the tutorials that I'm doing for Phys111 tomorrow.
Here.
Last week.
Here you go. What's your name?
Emma. Which
Do I have your? Do you have your card?
No.
No. Here, this is for you too.
Okay. And is this just to get into rooms?
Yeah.
And stuff? Okay.
That's right.
That
Any
might be helpful.
questions about this? Same
Kind
deal
of.
as
Yeah.
usual.
So what is it? What do they do? So I just give them
This
and-
one's vectors and then box counting.
Okay.
So count the area under each of these and then draw it. So this is the solution sheet.
Okay.
And then these are the question sheets, and they're also places to write their answers.
Okay. Perfect. And do you want them to do them in groups or separately or?
Yeah, tell them to do it in groups.
In groups. Okay. And then they're doing it all for 40 minutes together, and then for the last 10, 20 minutes,
Draw
everyone's marking
the
each
solutions
other's.
on the board, yeah.
I'm drawing the solutions on the board. Okay.
Anything else?
I think that may be it.
Do you know how to run a live stream on YouTube?
I do not. I know you did though.
No, it's going bad this time. Last year we had no problems, but this year the thing keeps dropping. Now we're offline again.
Oh, I have no clue.
I don't know either. All right.
Well, hopefully you get that fixed up again because that helped me a lot last year.
Oh, did it? I'm
Yes.
happy to hear that.
Yeah.
Do you want to tell the students how to help you?
Hmm?
Okay, talk to the mic.
No.
Okay.
Hi.
All right, get out of here.
Okay.
Hello. Yes, physics TAs. All right, where was I? Labeling this axes. 30, 40, 50, 60, 70, 80, 90, 100. 101, 102, 103, 104, 105. So 150, etc. All right, so we can just work off that. So, the deal with this question is sometimes we're drawing straight lines. I wonder if I can use a ruler on my tablet. Let's see. Got a soft, floppy ruler. Let's try it. I don't think anything's getting scratched. Do you like this? Yeah, no, not bad. Okay, let's change colors. Oh, we're in the money. Okay. So sometimes in this question it's telling us how much time it took. Sometimes it's telling us the slope, stuff like that. So, this is question number 55, right? Okay. So 10 millimeters per second, that's telling us about the slope of this. So it says for the first, so it's going to travel there until it reaches this line here. Okay. 10 millimeters per second is kind of one square like that. So I'm just going to line up my ruler on my graph paper. Oh, this almost works. This almost works. And draw the line. Oh, it's working. Nice. All right, so that green line, that's our position versus time for the first leg. Then it goes 6 millimeters per second and goes for another 3 seconds. So for the next 3 seconds to 3, it's going to go 6 millimeters per second. What does that look like? Looks kind of like that's where you get to about 18, which is about there. Oh, now you decide you don't want to auto turn into a straight line. Let's try this again. 18. It's about like that. All right. Stops for 4 seconds. That's easy. 1, 2, 3, 4. And then it walks backwards to its starting position at 8 millimeters per second. Oh, geez, what does 8 millimeters per second look like? 8 millimeters per second is like, well, I mean, it goes, we know that, oh, geez. We know that the top of this line here is 0.2 from the top. So 8 millimeters per second is from where this line ends to the next corner of the thing. So it goes like that. Oh, we're at a page. Oh, whatever. All right. So the next part of the question is, draw the x component of the velocity as a function of time. Well, you know, in this question, they've already given us the velocities. So I don't think it's going to be too bonkers. Let's see. 1, 2, 3, 4, 5. Yeah, we'll go to 5. All right. 1, 2, 3, 4, 5. Minus 5. 1, 2, 3, 4, 5. This one's plus 5. V meters per second, millimeters per second. So we don't want this to be 5, and we want it to be 10 seconds. 10, 8, 6, 4, 2, minus 2, minus 4, minus 6, minus 8, minus 10. All right. So for the first batch of time to this time, it's going at 10 meters per second, plus 10 meters per second. And then it goes at plus 6 millimeters per second, which is like that for 3 seconds. And then it's 0 for 4 seconds. Oh, now you want to be straight line. And then it's minus 8 for a bunch of seconds. And that's what the velocity as a function of time looks like. Hooray! Time to go to see if anybody's complaining about the poor quality of this feed. No, and nobody said that they can hear my voice. The one person watching. I wonder who they are. Maybe it's a bot. That'd be fun, right? Okay. Next question. So that's 55. Next question is, ooh, hello. 65. Question for 65 reads like this. A dragster's position as a function of time is given by x is equal to 3.0, no, sorry, there's no point there. 30.02 times t to the 3 over 2. Calculate its velocity at t is equal to 1 and t is equal to 4 seconds. This question's not so hard. All we do is we say the velocity is equal to the derivative of time. Ugh. Good. And I'm just going to use the power law. So power law says ignore coefficients. I'll just leave that aside. It says take the expression in the exponent. Oh, excuse me. And bring it down out front. 3 over 2. And then subtract 1 from it. So 3 over 2 minus 1 is 1 over 2. Let me rewrite this a little bit nicer. Calculon, don't fail me now. 30.2 divided by 2 times 3 is 45.3 times square root t. And now I'm going to evaluate t at the times. So the first one is 45.3 times square root of 1, which is 45.3. And the second one is 45.3 times square root of 4. So it's calculate 90.6. Ta-da! Any questions? Okay, so that's 65. 72. That's the next question. Is this an infinite canvas of oh, it is. It's an infinitely long sheet of graph paper. Is that great or what? I think that's pretty great. 72. In a foot race between two runners, is it possible for the second place finisher to have a greater speed at the finish line than the winner? The answer is yes. To understand the right answer, let me tell you the story of the tortoise and the hare. Once upon a time, there was a hare. A hare is a type of bunny. And there was a tortoise, which is, it's like a turtle, but it has feet instead of flippers. And the thing about tortoises is they're very slow, and the thing about hares is they're very fast. Well, they're quick. Quick like a bunny, as the expression goes. Okay. So the story is that both of them line up at the starting line. One day the hare was bragging in the woods about how he's the fastest person in the woods. And the tortoise was like, "Oh, I'm tired of you bragging all the time." And the hare is like, "Hey, I'm faster than you, old chum." And the tortoise is like, "Yeah, well, whatever." And so the rabbit was like, "Whoa, whatever." Actually, not a rabbit, a hare. They're different animals. Um, okay, so here's the finish line. Yay, finish line. And so the hare got sleepy and was like, "Oh, hey, I got this thing in the can. Look how far back the tortoise is." And the hare fell asleep. Under a tree. And the problem with that is that the hare stopped moving, but the tortoise did not. Oops. Gotta remember his body. The hare stopped moving, but the tortoise did not. So slowly, slowly, slowly. Oops, I've got the bottom end in there. Let's try it this way. Okay. Slowly, 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 the tortoise made his way down the race course, and the hare kept sleeping. And then the hare woke up. "Oh no," said the hare. "What am I gonna do?" Oh. The hare can't believe that he slept the entire day away. And so the hare gets up and starts getting going. But it's too late. The tortoise already beats him to the finish line. Oh, all right, this one. The tortoise already crosses. The moral of the story is, slow and steady wins the race. And there's a couple reasons I'm telling you this story. The first is that this particular way of explaining it, where you draw cartoons, isn't very illustrative of the facts in question. But if you draw a the motion diagram doesn't. But if you draw a graph of how the race goes, it actually kind of is. So that's x is equal to 0, and here's the finish line. Finish. The tortoise in green here travels at a constant velocity. It's not very big, but it crosses the finish line. The hare's trajectory is going to be more like this. I'm going to go really, really fast. Oh, time for a nap. Nap, 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 nap. Wakes up, tries to scoot, doesn't make it in time. Okay? The tortoise finishes first. The hare finishes. The tortoise finishes then. The hare finishes at a slightly later time. So, how do you interpret this in terms of velocity? Well, the slope of these curves is the velocity, right? So the slope of this is, constant. The slope of the hare is fast. It's much faster. Higher slope, faster speed, slows down, 0 velocity. Wakes up, accelerates. High velocity, high slope. But even then, even though you're traveling faster, you didn't cover nearly enough ground. So, hey, these these position versus time graphs are actually pretty useful. Well, there's another reason it's useful to talk about, which is that the school year, it's often kind of like this. So right now, we're in this part of the term. This tortoise is the amount of work we expect you to do over the course of the school year. And you'll know that every day the amount of work we ask isn't substantial. We just like a regular amount, but it keeps building. Number of concepts we ask you to learn about keeps building. The number of things we expect you to be able to do keeps increasing and increasing and increasing. So, you feel like you've got it all well in hand because it's the second week of school. If you proceed to party the whole time, sometimes you might have to cram at the end of the term. And that means that you get a C or a D or an F. It's better to just, stay on top of everything the whole time. Haha, isn't that fun? Yeah, so long story short, the velocity is not the same thing as the displacement. The velocity is not the same thing as the displacement. The thing that determines how much of a race you're in is the displacement. The velocity is related to the displacement, but it's not the same thing. It's the area under the velocity that's displacement, etc., etc., etc. Let's move to the next question. I mostly just wanted to draw pictures of rabbits. Okay, so that was question 72. Oh, you can zoom in. Dang, why aren't I zooming in the whole time? Okay, 72, and now it's time for question 85, and then we can go home. 85 question goes like this. Oh, cool. Okay, here's one thing you need to know. When I choose these questions, a lot of them are that I look up the questions that you've been assigned for the homework, and I try to find questions that are kind of like them. But sometimes I whimsically add random other questions to it. And for the most part, when we're doing this exercise, I'll do... Oh, our stream stopped. Oh, we're back up. So I'll do whatever question I list. And sometimes I choose... You'll note that in the book, you should open your book. It says there are little dots after each question, little blue circles. Those indicate the difficulty level. So if it has 1 dot, that means a fairly straightforward question. 2 dots means that it's kind of difficult, and 3 dots means that you really have to think. So sometimes I accidentally give myself 3-dot questions because, I contain multitudes just like anybody else, and some of my multitudes like watching others of my multitudes struggle on live internet feeds with weird questions. So I don't necessarily read them all the way through, like the ones that match the homework I do, but sometimes I'll... Anyway, this question's weird. It's about Zeno. Zeno's great. He belongs to a school of philosophy, the pre-Socratics. Pre-Socratic philosophers had a great time because this was before logic was invented. Logic was formalized by Aristotle, as you know. I don't know if you knew. There's like Socrates, and then Plato was his student, and then Aristotle was Plato's student. Plato started a school called the Academy. Aristotle was the guy who invented logic. He didn't invent it, but he formalized it. And before then, there were all sorts of methods that people would use to decide whether a particular philosophical argument was reasonable or not. And so there were several schools of Socratic thought. Maybe you've heard of Democritus. He was the guy who said that everything was atoms. There is a guy called Parmenides. A guy called Heraclitus. Bunch of really cool guys. You can take a whole course on these. I love them. Okay. So the deal here is that all these different philosophers had these crazy different ideas. And there was one philosopher who said, everything in the universe is changing. One of the big aspects of this type of philosophy is they wanted to figure out which what was the essence of physical reality? What was the essence of our universe? You know, so like some pre-Socratic philosopher would be like, everything in the universe is fire. So water is just a type of really, really condensed fire. And fire and somebody else would be like, no, everything is made out of water. Fire is just really, 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 really hot water. And there's vapor and then regular water. And then like wood and stuff is made out of water. And the fire people would be like, no, wood's made out of fire. That's why you can burn it. Anyway, they go back and forth. And it got fairly philosophy. It got fairly philosophical. Some of them were like, oh, everything is made out of love. Love is the thing that makes our universe what it is. And others would say, no, change is what makes our universe our universe. So Zeno belonged to a school of philosophy that said that change didn't exist. And that all change, everything we would describe as something changing in our universe, was an illusion. Because, you know, you can be wrong about things. And if you're wrong, you're like, oh, well, it wasn't me that was wrong. I saw something and I misinterpreted it. It was an illusion. So what we're seeing is change. We're misinterpreting things. And he had a couple really fun paradoxes. The way he did his arguing was he said, I'm going to propose some scenarios that sound reasonable, but then when you really think about it, it turns out that there's something that doesn't fit. It's incongruous. This is one of Zeno's paradox. Okay, so it says a runner has to run a race of length d. At the instant that is a time interval, delta t at the start, he's half the distance from the finish line. Let's draw this picture. So there's our interval d, and then at t is equal to delta t, whatever that is, some time interval, he's halfway. He's right there. He's living on a prayer. So he's that distance from the finish line. And then you're like, oh, well, then he gets to the finish line. And Zeno goes, no, you know, before he reaches there, he has to reach this point, which is d over 4, delta t over 8, etc. So if you read the question, it spells this all out. So I'm going to get back to reading this question. It says, this description of the motion is an infinite series of smaller and smaller displacements. The paradox is that the analysis suggests the runner will never make it to the finish line, even though we know he does. I guess Eric Mazur doesn't believe in pre-Socratic Greek philosophy. Incidentally, this picture hasn't really updated in a while. Is this doing good? Oh, jeez. All right, let me try rebooting this. Oh, you missed me. You missed me writing all the pre-Socratic junk. Okay, well, and also this screen is too big. Let me try resizing it. Okay. All right. Okay, you missed all these drawings. Long and the short of this is that Zeno's paradox, Zeno actually had 3 paradoxes. One of them involved Achilles and a turtle, and it was actually kind of like this, only, yeah. Another one involved shooting an arrow at something. I forget what the third one involved. But the long and the short of it is, Zeno came up with 3 paradoxes, each of them involving something we know has a beginning and a middle and an end, something that evolves in time, like a runner running a race. And the idea is that you say, oh, can a runner win a race? Yes, the runner can win a race. They just start here and they end here. But Zeno goes, well, before they can get all the way here, they get halfway. And you go, yeah, but then they go from halfway to the end. And they go, no, before you go from here to the end, you have to go halfway again. You go, yeah, but then you just go from here to here, right? And really easy jaunt. No, no, no. Before, there's still a halfway point that he needs to reach. And there's still a halfway point that he needs to reach. And there's still a halfway point that he needs to reach. And on and on and on. And he has an infinite number of halfway points to reach, and he never gets to the end. And so you go, well, I guess the runner can never finish the race. I guess motion doesn't exist. Well, that's sad. So how are you going to deal with this? The deal here is that the reason we have trouble with this is that there's actually an infinite number of steps involved. And there is. You all are taking calculus right now. You're familiar with arguments that involve an infinite number of things, right? So when you take a derivative, you're taking the slope of the secant line and essentially making the interval width 0, infinitesimally small. And that's a very similar, actually, type of argument to the one that we're doing right here, right now. And kind of the formalization about talking about infinitesimals and the formalization about talking about adding an infinite number of infinitely small things to get a finite thing, that was something that, that was a branch of mathematics, certainly, that the Greeks had no notion of. So, I mean, Eric Mazur's introducing this idea in his textbook because he wants us to laugh at it. Ha ha ha. But it's actually pretty clever because the distance the runner has to travel is d over 2 plus d over 4, that's reaching the second midpoint, plus d over 8, that's reaching the third midpoint, plus d over 16, that's reaching the fourth, plus d over 32, plus d over 64, plus d over 128, plus and on, and on, and on, and on. Infinite number. How are you going to sum up these infinite things? And yet we know all these things add up to d, right? Also, the amount of time that's passed is, let's see, what do they say? The first time takes delta t to run. The second time takes delta t over 2. The third time takes delta t over 3. Nope, not 3. 4. The fourth leg takes delta t over 8. The fifth one takes delta t over 16. And on and on and on. So it takes an infinite amount of, I mean, does it take a finite amount of time or an infinite amount of time? Because there's an infinite, this series is an infinitely long number. And like I said, we had no notion once upon a time whether or not this would add up to some finite number. Since then, we have actually mathematically gotten a much better grasp of these infinite sums, and so you can say definitely that this thing adds up to d. This thing adds up to 2 delta t. So the runner's speed is constant. It's going to be d over 2 divided by delta t, which is d over 2 delta t. And if you do it this way, you get d over 2 delta t. So you can use it with any of these intervals, or alternatively, because we're assuming they're traveling at a constant velocity, you can use any partial sum. So you can do the first 4 and divide it by the first 4 times, and you'll always end up with the same thing. Which is a little bit weird and counterintuitive. Usually when things add up like this, they don't cancel out, but don't worry about it. So that's the runner speed. What time interval is needed for the trip? 2 delta t. How do I know that? How do I know that? I know it because, I mean, okay, so let's imagine you have a box that's 1 square. 1 by 1. What's the area of this box? It's 1. We can cut this box up into different pieces, though. Let's say you cut it in half. What's the area of each square? This one's a half, and the other's a half. Then you take the second square and you cut it in half. What's its area? quarter. You take the remaining box, cut it in half. What's its area? 8. You take the remaining chunk, cut it in half. Its area is 16. Cut the remaining one in half. 1 over 32, 64, 198, etc., 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 until you get... You can keep doing this infinitely long, yeah, at least as an idea. And what this means is, if you then add up all these different little pieces, it'll be the first piece plus the second square plus the third square plus the fourth square, etc. So 1 is equal to 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64, etc. Right? And this particular sum shows up in two places in our sum. So the first, d over 4 plus d over 8 plus d over 16 plus d over 32. So this is the sum of all the distances that we've traveled. We can factor a d out, and we get 1 over 2 plus 1 over 4 plus 1 over 8. We can factor a d out because each of these terms has a d in it. Plus 1 over 16 plus 1 over 32, right? And so all of these add up, according to this argument, to 1. So that's d. As for the amount of time it took delta t to run the first bit. It took delta t over 2 to run the second interval, delta t over 4 to run the third interval, delta t over 8 to run the fourth, delta t over 16 to run the fifth, delta t over 32 to run the second, etc. Okay? I want you to note that when we split this one out, we don't quite factor it. We split it up like this. We're going to add up all these together, and then we're going to put this one aside. Delta t plus, and then all of these terms have a delta t term in it. I could factor that out, so it becomes 1 over 2 plus 1 over 4, 1 over 8 plus 1, etc. Okay? So all of these together add up to 1. So this is delta t plus delta t, which is equal to 2 delta t. That's fun, right? I'm having fun. Let's see if anybody's mentioned anything in the comments. Nobody's mentioned anything in the comments. Okay, but for some reason the stream is very healthy. Okay, so what's the third question? Describe the resolution of this seeming paradox. Oh, come on. Merrick Mazur. The resolution to this paradox involves the fact that you can add up an infinite series of things and get a finite amount. That's not something that the Greeks knew, and it's certainly not something that's always true, right? I mean, you can try this one yourselves. 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6, right? This is a bunch of things being added together where each one gets smaller than the last. But if you add that up all the way to infinity, this number is infinite. I know, right? There's a mathematical proof for that. It's pretty fun. But I'm not going to teach it to you because I don't want to. It's a different course. No, what do? You, I think you can combine them in pairs. No, you add them up in sums. Anyway, if you want to see the proof that this is infinite, take Math 101. The last couple of school we talk about. It's a pretty fun little proof. But long and the short of it is, there are some infinite sums that add up to a finite number, and there are some infinite sums that don't add up to a finite number. And it's not obvious which one is which. So it's not obvious on face value if you have an infinite number of things and you add them up, that whether it's going to be finite or infinite. So the thing about this particular paradox is that when somebody tells you that you have an infinite number of things to do, you usually assume that it's going to take you an infinite amount of time. And that assumption is usually fair, right? But in this case, each successive step to it takes less and less time, right? So to go the first 2 midpoints, it takes you this much time. But then to go the next midpoint, it takes you less time, and the next midpoint, it takes you less time, and the next midpoint, it takes you less time. And the marvelous thing about the math in this situation, the nice thing about our universe maybe, is that both of these infinite sums add up to finite numbers. I'm not sure if that's necessarily the case. It's definitely true, and it's the reason why these things work mathematically. Don't get too caught up in this. I mean, it is philosophy. At the heart of it, it's just kind of we needed to get a better understanding of infinite things and also infinitely small intervals to be able to invent calculus. And calculus is kind of the mathematical revolution that allows us to talk about physics at all. So I think Mazur's being a little bit smug in this book. Certainly he didn't write the solution in the answer to review questions. So, but yeah, it's just fun. Zeno's fun. It's worth it if you take a couple fun, weird courses that aren't just plain Jane science courses. You take some philosophy, you take some history in life, you'll have a better time. All right, well, that's it for this week. I've talked for 50 minutes. Well, to be honest, I talked for about 40 minutes about physics, and I've talked for about 10 minutes about streaming videos and technical issues, and then I talked for 10 minutes about Greek philosophy. So, have a nice day. I'll talk to you later. Next week, there'll be more difficult questions, so I probably won't waste as much time. See ya.